Hello, in this video we will use the following Google Sheet functions: complex, IMABS, IMARGUMENT, square root, sum square, and transpose. Here we have three pairs of numbers. We have the real number 1 and 2.5 as the imaginary. Second pair 0 is the real number and 4 is the imaginary. And the third pair 3 is the real component and negative 1 as the imaginary. We will use complex and the and calculate the magnitude, the square root, and the angle between the vector projecting from the origin to each of these points. So we begin with drawing the showing the number this pair of numbers in the scatter chart. So we transpose it and insert the scatter chart. And so here we have a scatter chart where the horizontal component is the real component and the vertical component is the imaginary component. In this chart, we have 2.1 and 2.5, which is the first pair. The second pair is 0 and 4, and the third pair is 3 and negative 1. So we can now complete or calculate the complex function of each of these pair. Let's start with the first pair. Complex real component is 1, imaginary component is 2.5. Here we have 1 plus 2.5i. In the second pair, we have again complex 0 as the real component, 4 as the imaginary component. We have 4i, 0 plus 4i. And the third pair is again complex, where we have 3 as the real component, the imaginary component is negative 1. So we have 3 minus I. Next, we use IMABS to calculate for the distance between the origin 0 to the first point, which is 1 plus 2.5i. So from the origin to this point. So we will calculate the distance using the hypotenuse of the Pythagorean formula. Or we can use first with IMABS. IMABS of this number. So we have 2.69. That's the distance between the origin to this point. Next, the distance between the origin to 0 plus 4i from here to this origin. So this is again IMABS of this number. So the distance between the origin to 4i is 4. Next, we calculate the distance between the origin and this point. So the origin to the point 3 minus I. So this is equal to IMABS and the distance now is 3.162. So this is the distance. We can use the hypotenuse of the Pythagorean formula using square root sum square. So we have square root sum square of the real component, and the imaginary component. We get the same result. Likewise, we use the hypotenuse of the Pythagorean formula, which is equal to square root of sum square of the r and the x, or the real and the imaginary component. So you have 4. And the third pair, we use the same hypotenuse formula, square root sum square of the real component and the imaginary component. So we still get the same value. Now that we have calculated the distances from the origin to each of these points, we can now calculate the angle between the horizontal and the vector projecting to each of these points. So this 2.692 vector is this vector from 0 to the point 1 plus 2.5i. So we'll calculate that in radians. So we use the im argument. Im argument, that's im argument of the complex number. So that's the angle in radians, 1.19. That can be converted to degrees, which is times 180 divided by pi. So the angle between the vector projecting from 0 to this point is 68.19 degrees. So that's the angle between the horizontal and the vector projecting from here to this point. Next, we calculate the angle of the second pair. So we use im argument of 4i. That is 1.57. So we can change that to degrees, which is equal to this number, that same number times 180 divided by pi. And the answer is 90 degrees. So it's perpendicular. So the vector projecting from the origin to this point is 90 degrees. So it is perpendicular. Next, we calculate the angle of the vector projecting from the origin to this point with the horizontal. So this is equal to, again, im equals im argument of this complex number, that is negative 0.321 radians. Convert that to degrees. That's the number times 180 divided by pi. And that is negative 18.43 degrees. So the angle between the horizontal and the projection from the origin to this number with the horizontal is negative 18.43 degrees.